we have now extended the kernel language with cells. Let's now extend the abstract machine to explain how cells execute. So in the new abstract machine, there are two stores. In addition to the single assignment store that we know already, we will have a second store called the multiple assignment store. So the single assignment store contains variables that can be only assigned to one value, so it's called the immutable store. And the multiple assignment store contains cells. Since they can be assigned multiple times, we call this the mutable store. So in the mutable store, a cell is a pair of two variables. The first variable is bound to the name of the cell, so this is a constant. And the second variable is the cell's content. This can be any variable in single assignment store, even the name of another cell, or even the name of the cell itself. So when we assign a cell to a new content, the pair is changed. In fact, the second variable in the pair is replaced by another variable, any variable. The first variable always stays the same. Okay, so that's the assignment. Warning here. When we assign a cell, variables in the single assignment store do not change their value. When we change the content of a cell, we are just changing which variable is the second variable in the pair. We're not changing anything in the variables themselves. Okay, that's important. So here's an example. So the full store here, sigma, has two parts. Sigma 1 is a single assignment store with variables t, u, v, etc., x, y, z, w. And the multiple assignment store contains the cells. So it contains these pairs. So the first pair is x colon t, and the second pair is y colon w. So in this particular sigma 2, there are two cells, x and y. The name of the x is the constant xi. We use a Greek letter for this in order not to confuse this constant with the two other kinds of constants that we have, which are numbers and atoms. So cell names are another kind of constant, and we will use Greek letters to signify them. So the name of x is xi, and the name of y here is zeta. So when I do the operation x colon equal z, I will change the pair little x, little t into little x, little z. So I've replaced the little t by a little z. So that's an assignment. Now the operation of read or accessing y, will return the variable w. This is the second variable in the pair y. So all of this is assuming that we have an environment which is a trivial one where all the identifiers refer to variables which are just the smaller case versions. Okay, so that gives us the semantics of the imperative paradigm. Now, by adding cells, we have left the functional paradigm. We are no longer doing functional programming, and we have entered a new paradigm called the imperative paradigm. So the imperative paradigm is the functional paradigm plus the cells. So the interesting point about the new imperative paradigm is that it allows programs to express, observe growth and change in themselves. And this gives new ways of thinking that were simply not possible in the functional paradigm. For example, the imperative paradigm is the foundation of object-oriented programming, which contains many new ways of structuring programs and principles that are important for building large systems. This is all possible in the imperative paradigm and not in the functional paradigm. So the kernel language of the imperative paradigm consists of the instructions in the functional paradigm plus three new instructions. So the creation of a cell, the assignment, and the reading or access of a cell. So this is the complete kernel language of the imperative paradigm. In fact, there's a second equivalent way of representing this kernel language. Here's the second version. The second version has two new operations instead of three. An operation called new cell, the same as before, and a new operation called exchange. In fact, the exchange here does both an assignment and an access atomically, which means together as one operation in one step. So the exchange has three arguments. So x is a cell, Y is bound to the old value of the cell, and Z is the new value of the cell. So this second version of the kernel language of the imperative paradigm is equally expressive. In fact, it's possible to express exchange using access and assignment, and vice versa. Access and assignment can be expressed using exchange. It's an interesting exercise. But this second version is more convenient for concurrent programming. So we won't be doing that so much with cells in this course, but if you go on to do more sophisticated forms of concurrent programming using, for example, transactions or monitors, then the exchange version is much easier. But in fact, for this course, we can keep the original version here of the kernel language for the imperative paradigm, where we have 3 new operations for cells.